Hello, everyone. Welcome to the talk. I'm Zhihao Yuan, an HPC engineer from SimpleRose Inc. SimpleRose is a startup that produces linear programming and mixed integer programming solvers. But we won't be talking about matrices this time. Today's topic is about a less known utility in the standard library called reference wrapper. So let's start with thinking about this question. How would you switch between objects? If you're using Python, because in Python, every variable is just some reference that points to some object. By saying switch between objects, you can just assign different objects to the same variable. Can we do the same thing with C++ using C++ references? Seems not. Because to C++ reference, once it is bound to an object, it cannot bind to a different object. C++ reference can only be bound once. This does not mean, however, you cannot conditionally bind different objects to a C++ reference. If your control flow allows, you can do something like this. But in the most general case, we need some other thoughts. So, reference is just a pointer with a different syntax, roughly. Pretty much everything reference can do can be done with pointers. So why don't we try pointers? It works, gives you the right semantics, but hey, it's modern C++. No more raw pointers. Let's make it smart. Then we ended up with this. I saw that in some production code. I can't say that it doesn't work. It works and it's modern, but So let's look back a little bit. When talking about reference assignment, what do we really mean? In Python, every time you see an assignment operator, it binds some object to the variable. But the thing is getting a little bit inconsistent in C++. To a C++ reference, initialization binds the object to the reference, but assignment assigns to the bounded object. This behavior is called assign through. Now, think about this. What if we have initialization and assignment both binding object? So initialization binds the object to the reference, and assignment rebinds a different object to the reference. Just like Python or Java, without garbage collection, of course. With this semantics, we offer std reference wrapper. If we rewrite the previous example that didn't work by replacing the autoref with reference wrapper, the example works and has the right semantics. So reference wrapper models rebindable references. However, it is a standard library utility. It's not something built into the language. But we put lots of thoughts in making it closely matches language air value references semantics. Behavior. For example, reference wrapper may refer to const objects, and it does not bind to R-value expressions. Declaring a reference wrapper T does not order use T. This essentially means that T may be an incomplete type, but I will explain this more later. Let's start with the first bullet. So in order to produce a reference wrapper that refers to some const qualified AR value, we can rely on class template argument deduction. In this example, if you initialize a reference wrapper from a const value, the type of the reference wrapper is deduced to reference wrapper int const. Now, if the expression to initialize reference wrapper is not a const value, what if it is non-const? Well, we can turn it into a const one by using stud as const. This mod utility is introduced in C++ 20. Next bullet, reference wrapper only binds to error value. So if you recall what does the user-defined literal operator s does, it creates a temporary object of stud string, which is a PR value. Because reference wrapper only binds to error value, this doesn't compile. The language error value reference doesn't compile in this case either. How about reference wrapper tconst? Does that bind to R values? Nope, because otherwise you'll be getting a dangling reference. But this time, its behavior slightly diverges from what language error value reference has. Because to language error value references, there is something called lifetime extension. This is introduced before we having R value references. So from some point of view, it's trickier than necessary. Reference wrapper didn't copy this behavior. Reference wrapper may refer to an incomplete type. So when we're talking about incomplete type, we mean something like this, a user-defined type that only has a declaration, where its definition is hidden in some other translation units. But given this, a user will be able to form a language error value reference to that type and use that in a parameter list when declaring a function. You can do the same thing with reference wrapper as well. This guarantee is provided in C++ 20. But as far as I know, all standard library implementations guarantees this since C++ 17. Reference wrapper is not only rebindable. It also does assign through. So if we bring back the previous example, you will notice that this line compiles while we are changing autoref to reference wrapper. This is because reference wrapper T is convertible to tref. This conversion can give you direct access to the bounded object, but you don't have to rely on this conversion to get that access. You can also reach the bounded object using the .getMember function right here. With this, we are able to combine rebinding and assign through in the same program. When you want to rebind that object to a reference wrapper, you use reference wrapper's own assignment operator. If you want to assign to the bounded object, you can use the .getMember function to reach the bounded object and use that object's own assignment operator. So what's the use of this? Let's talk about linked list. Here's a very simple linked list where its node just has a next pointer and a string value. And the main body of the linked list consists of a head pointer that points to the first node. The question here is, how do we implement a remove function? Note that the remove function here should remove every node where its string value compares equal to the string passed into the remove some function. Before we jump into these algorithms, I want to introduce a tiny little trick. So we need to drop nodes from linked list, which means we will need to delete them. But assuming that a node is created using the new operator. But the delete operator also destructs the node, which means after the destructor being called, you can no longer reach the next member of a destructed object through a pointer that used to point to it. So this code doesn't work. What works? This works. We can save the pointer, skip the node, and then delete the current node using the saved pointer. With the help of standard library utilities, we can replace these 3 lines with just 1 line. Stud exchange. What it does is that it is essentially similar to an assignment, but after it assigns the right-hand side to the left-hand side, it returns the previous value of the left-hand side, which allows us to call delete operator on it. This small utility is introduced in C++ 14. I hope you enjoy it. So now let's talk about some algorithms. Here's a very simple one. We need to drop nodes. We can do so by changing the previous node's next member. So in the loop, we keep our current node starting with letting it point to the head first node, and then we always keep the previous node as last. When the current node is head, there's no last node, so the last is non-putter in that case. And in the body of the loop, we try find a match. If we find a match, if there is a previous node, we skip the current node using previous node. If there's no previous node, we are able to directly modify head. After done that, we delete the current node. Continue. If we don't find a match, we assign the current node to the previous node to save it and move forward to the next node. So this is a rather naive algorithm. Is there anything we can do to simplify it using the things learned today? Here are some thoughts. We will directly modify head as if we have an L value reference that points to the head, right? Can we form a reference to pointer for each current node so that we can directly modify every current node in the same way modifying head? And yes, we can do so by rebinding the reference to head to every other node. So we start with binding a reference wrapper, start with binding the head to a reference wrapper. And while we are going iterating, if we found a match, we can perform relinking by replacing the current node with the next node. When we don't have a match, we continue iterating by rebinding the reference to the next node. So that's the entire algorithm for remove. You can compare this algorithm with this one that is written using pointer to pointers. It even has a name called two-star programming. And Linus even said this kind of code is written by people who understand pointers. I would recommend these experts stop drawing lines behind themselves. You may understand pointers, but you don't understand rebindable reference. To me, pointers have very mixed semantics. The following material are stolen from Walter E. Brown. If you come to CPPCon but don't know who him is, please look up his video on YouTube. So Walter says, a pointer value is a value of a pointer variable. Just like all variables values, a pointer value is an R value. What does this mean here is that a pointer value is something like 0x001, that's a R value. But unlike R values of other types, a pointer value can be treated as an L value if you dereference it. A pointee is a variable whose L value corresponds to the R value of some pointer variable. A pointee is what you get if you dereference it. Given these backgrounds, a pointer value is simultaneously an L value from the pointee's perspective and an R value from the pointer variable's perspective. Which means the so-called two-star programming made use of these semantics, while reference wrapper made them explicit. Let's give this idea a little more practice. Still, the linked list. This time, how do we implement a function that reads from a file, one line per node? Note that we'll be using std_getLine to do this. And here's the answer. Same as before, we start with binding head to a reference wrapper and rebind that in each iteration. The only difference is that this time we are able to form a new node for each line we read and assign that node directly to the current node we are visiting. So far, is there any questions? Let me see. Why there's no not non pointer? In many cases, it will be a good substitution for reference wrapper. I think the pointer still has pointer semantics, right? It's still simultaneously an L value and R value. So that's still different. Okay, let's go back to the talk. Last topic. You probably have seen code like this. Function pointers. We start with creating function pointers from some function, and in some condition, we can assign the function assign different function pointer to, assign different function to the function pointer, and then achieve the effect of calling functions conditionally by calling the function pointer. So if you think about this example, function pointers, it is essentially a rebindable reference in the language because, first, its usage models after references. You don't need to dereference a function pointer in order to call it. You can just call it using the ordinary function call syntax. And this syntax is shared by reference to function. Not only that, it is rebindable using a simple assignment. So we have a rebindable reference in the language already. So going back to this program, if we replace auto with reference wrapper, you'll find that the program still works. because we provide a call operator to reference wrapper. Reference wrapper works as a function pointer as well, only better. Because again, we made it closely matches function pointer's capability. And reference wrapper extends the scope of pointing to callable objects, not only functions. And it's not nullable. So what do I mean by saying it closely matches function pointer's capability? I'll give you some examples. First, the reference wrapper works in const expr. You can use that in a const expr function, bind the reference wrapper to a const expr function, and finally, you can even call it in a call const expr context, just like function pointers. This guarantee is given in C++ 20. If your standard library vendor hasn't implemented, you're welcome to contribute. Not only that, reference wrapper's call operator is also properly constrained to make it behave like function pointers. So if you have some original function and a reference wrapper to that function, if you test is invocable of the original function given using a set of argument types, if is invocable answers yes, its reference to the original function, its reference wrapper also answers yes. If is invocable answers no, reference wrapper answers no as well. So callable objects, do you mean pointer to members? Well, yes and no. Reference wrapper can bind to L-value pointer to members and call them with the ordinary function call syntax. But if you recall what pointer to members are, they are usually PR values. The problem here is that when we are saying reference wrapper models after reference to functions, we mean that it can point to functions. But to pointer to members, you can't really form a reference to member because pointer to member has no pointer. There's no such entity in the language called member that you point to. So it works, but probably not in the way you are looking for. Stud memfun is probably what you're looking for. But it does work well with user-defined callable objects. So if you have two callable objects of the same type, you can switch between them using reference wrapper just fine. But this does not mean, however, reference wrapper can do everything. If your callable objects are of different types, you won't be able to switch between them using reference wrapper because reference wrapper does not erase the pointers type. We can ask stud function to erase the types though. So this is an extremely rarely used feature. The background is that stud function starts with value semantics. But if you assign reference wrapper to something, to stud function, it behaves as if it has reference semantics. But let's look back what we're looking for here. All we need is just a rebindable reference to functions, and it should be a type erasure, right? Why don't we just provide it? A type erased rebindable reference to functions. Stud function ref. We are going to have it in C++ 23. So to summarize what can replace function pointers, today we learned reference wrapper, that is non-non. Function ref is nullable as of today, although I don't know why. Stud function is nullable. Reference wrapper has reference semantics, so does function ref. Stud function has value semantics. Reference wrapper does not erase the pointers type. Function ref and stud function perform type erase. But reference wrapper is the smallest of the all three. Its size is as large as a pointer size. Function ref is at least 2x that size, and stud function is only larger. Here's a summary of what we learned today. Reference wrapper is a rebindable reference. It makes reference binding and assign through explicit. This even allows you to mix these semantics in the same program. And reference wrapper is a better function pointer. Question time. Let me see. Q&A. How does performance of reference wrapper compare to a raw reference? I think roughly the same, because reference wrapper just has a pointer inside. How do I? Why there's that I answered this question? Okay. Do you have more questions? If not, I have a ask me anything session right after this session in this room. You're welcome to join and ask me more questions.